Welcome to Logical Verification 2020 to 2021. In this video, we're going to cover Chapter 13, Section 1, the construction of the rational numbers. So, 2 chapters back, in Chapter 11, we saw the construction of the integers. And now we're going to do a very, very similar construction to create the rational numbers inside Lee. We're again going to use a quotient. So a rational number is a fraction of 2 integers. And this follows the same pattern that we saw with the integers. We thought the integers are really the natural numbers plus the minus operation, and there we represented every integer as a difference of 2 natural numbers. And now we will define the rational numbers in a very similar way, essentially with the idea that the rational numbers are the integers plus the division operation. Okay, so this is very similar construction, and for the integers we considered pairs of natural numbers as the base type for the quotient, but for the rational numbers we have one more restriction here, namely that the b should be non-zero, and hence we pack the a, the b, and this condition together in a convenient type that we call fraction. And then we will proceed in very much a similar way as we constructed the integers. We first define an equivalence relation on fractions that tells us when 2 fractions should be equal. So we're kind of wondering when should a over b be equal to c divided by d. And we'll do this using the same trick as before. We multiply both sides by b and d. And then we get that a times d is c times b as the appropriate equivalence relation on fractions. Note again that this is really just an equality that is defined in terms of integers. And just as in the integers, these pairs of natural numbers and these fractions, they are not unique. Several fractions denote the same rational number. So 2 divided by 3 denotes the same should denote the same rational number as minus 6 divided by minus 9. So these equivalence classes, they contain more than one element, more than one fraction. Okay, so let's look at how this looks like in Lean. First of all, we start with this fraction structure, which contains the numerator, the thing above the fraction line, the denominator, the thing below the fraction line, and a proof that the denominator is not 0. This is what we call a fraction. And then we will define all operations on fractions. So we will define it as the 0 fract, we will define the addition of fractions, so as an operation, as a binary operation that takes 2 fractions and returns a fraction, and we will define an equivalence relation on fractions that corresponds to the equality of rational numbers. And then finally, we just lift everything that we've defined so far, all the stuff that we've defined on fraction, the additional fractions, to the quotient. The quotient that is obtained by the equivalence relation on fractions, and all the operations that we have defined on fractions will then be lifted to the quotient. Okay, so we have now defined what a fraction is. This corresponds to the pair of natural numbers we have for the integers. And then we define the equivalence relation on it. which is the thing that I've motivated on the drawing. We define the equivalence of two fractions while the equality of multiplication of integers. Okay, so this is exactly what I've drawn before. And now we need to prove that it's an equivalence relation, so that it is reflexive, symmetric, and transitive. Again, we restate the definition of the equivalence relation for convenience. Okay, so now we have defined fractions and the equivalence relation on them, and now we define all the operations that we want on the fraction type. We are not yet talking about quotients. This will happen at the very end. Okay, so first of all, we write a function that takes an integer and maps it to a fraction representing this integer. So we map the integer I to the fraction I divided by 1. So which means it has the numerator I, it has the denominator 1, and the proof is by sim. So we need to prove 1 not equals 0. Okay, so we know how to convert an integer into a fraction. And now we define what the 0. 0 is the 0 integer lifted into a fraction. 1 is integer 1 lifted into a fraction. And now we define an addition operation on fractions. So this might look scary, this definition here, but you can derive it yourself using the same trick as the same approach we took here for the equality. We just need to look at the addition of two fractions and then calculate with them as if they were actual rational numbers, and then we'll get some expression that we can use in the definition of our operation. We still need to prove that it has all the nice properties, but this is the way how you derive these equations in the first place. So what do? We multiply the left fraction by d and the right fraction by b. So what do we get here? We get a times b over, a times d over b times d plus c times b divided by c times d. Well, you can't see this. This is bad. So let me just redraw this. Again, so we want to figure out how to define the addition of two fractions. For this, we write down the fraction as it is. So we have addition of two fractions, and then we calculate with it as if we already had the rational numbers. So we multiply the left fraction by d. So b times d, and multiply the right fraction, both the numerator and the denominator, by b. Okay, and now we can add them. Over bd. Good. Okay, and now this is the definition that we're going to use for the addition. And yes, it looks very much the same. So, like above, we've got sum of the numerator of one fraction multiplied by the denominator of the other fraction. So a is a numerator and d is the denominator of the other fraction. So yes, this is indeed the definition that we want. Okay, and now we still need to prove that the denominator is not equal to 0, so that we have a valid fraction. And this follows using the not equal 0 lemma. So because on integers we have that multiplication of two integers is non-zero if and only if both of them are non-zero. And again, we restate the definition of the operation using lemmas, as this makes reasoning easier. In the last step, we will be lifting all these operations to the quotient, and for this we will need lemmas to tell us that, for example, the addition operation takes equivalent fractions and returns an equivalent fraction for equivalent fractions as inputs. So if the input fractions are equivalent, the output fractions are also equivalent, which is exactly what we're stating here. If we have fractions a prime, b prime, where a is equivalent to a prime and b is equivalent to b prime, then their sum is also equivalent. And there is one new tactic here that is interesting, and this is this AC raffle tactic, which, as the name says, is reflexivity modulo associative commutative reordering. So it can reparenthesize terms, so for example here the multiplication, and it can also commute, so permute terms in a multiplication. Okay, and so we now have 0, we have 1, we have addition, and then we just continue in this way. We do negation, we do multiplication, and then at some point we will come to something more interesting, the first operation that actually is new under rational numbers, namely the inverse. So one thing that is maybe important to mention here is that in contrast to mathematics, in Lean, the inverses and the division is defined for all inputs. In particular, there is the inverse of 0, and this is completely well defined, and we always say that it is 0. So this may sound strange because in mathematics, or maybe also in programming languages, we typically say that division by 0 or taking the inverse of 0 is undefined or gives an exception or something. But in formalized mathematics, it's very useful to have total definitions. First of all, we don't need to think about, we don't need to prove that the inputs to the inverse are well defined, that they're non-zero. This is one thing that we don't need to do if we have total definitions. And another one is that there are useful lemmas that we can prove about the total version, which return where division by 0 is well defined. For example, one thing that is true for division by 0 is x times x divided by x is x. So this is true for all x in the rational numbers, but only if we define the inverse of 0 as 0. So this is really a good choice, and this is also the choice that we're taking here. So we define the inverse of a fraction. So if we think about what it should be, the inverse of a fraction should, obviously be just swapping the denominator and numerator. And this is also what happens in the case that the fraction is not 0. However, if the fraction is 0, so that if we have a fraction 0 divided by something else, then we return 0. Okay? So now we can still restate the definition. Now with two cases, we now need always to distinguish whether the numerator is 0 or not. But everything else works exactly like for addition. We prove that it respects the equivalence relation. And now we have operations on rational numbers, and we can lift them to the quotient. So we define the quotient of the rational numbers by the setoid on the fractions. So this is the setoid that we've defined by the equivalence relation on the fractions. And now we just lift each of those operations that we had defined on the fractions, like 0, like 1, like plus, like negation, like the inverse, and get corresponding operations on the quotients. For binary operations like addition and the unit operation like negation, we need to prove that they respect the equivalence relation, but we've also proved this on the fractions. So defining the operations on the quotient is now very easy. For example, for addition, we use quotient.live2, which takes two fractions and returns the equivalence class of the addition of the fractions. And now we just need to prove that if the input fractions are equivalent, then the equivalence class of the output fractions are equal, but we know that equality of equivalence classes is the same as equivalence. This is the key property of quotients, so which we have here in the quotient.sound lemma. Now, this is something we've already proven, that if A is equivalent to A prime and B is equivalent to B prime, then the sums are also equivalent. Right, and the rest, the negation, the multiplication, the inverses, are defined in exactly the same way. Good. So just as for integers, using a quotient is not the only possible way to define rational numbers. We can also use subtypes, where we say that some fractions are canonical. For example, we might require the fraction to be fully reduced. So maybe as an example, so as I've said above here, we often have multiple fractions that can denote the same rational number, and then we say that we do not want fractions that are larger than necessary, but we only want fractions that are as small as possible. And then we define the rational numbers as the subtype of those fully reduced, of those the smallest possible fractions. So there is a certain advantage in using subtypes. As with the integers, one advantage is that you do not need to worry about lifting. Lifting in quotients is always a bit technically awkward, because in order to lift an operation, you always need to write down a proof that it respects the equivalent relation. While if you have a subtype, you can just access the numerator and denominator without any kind of proof whatsoever. Another advantage of subtypes lies in the way the lean virtual machine operates. So both subtypes and quotients are evaluated in the virtual machine as operations on the underlying type. So both the quotient.make operation and the subtype.make operation don't do anything at all. And like the way the code is actually executed in the virtual machine is by working on the underlying type. So if we work on a quotient, the multiplication of rational numbers will work with whatever fraction you used as an input, even if this fraction is unnecessarily large. However, if you use a subtype, if you evaluate the multiplication operation, the VM, it will always use this maximal reduced fraction, which can be faster.